Okay, so thermal energy. This topic covers areas in which heat and temperature effects can be measured and how heat energy affects different materials and substances. The movement of particles are also explained in this unit through the kinetic theory, and this leads to explanations of physical laws relating to the properties of gases and how much things heat up. Firstly, to begin understanding this topic, we need to understand the meaning of temperature. What is temperature? This can be explained through the kinetic theory, which states, when energy is supplied to an object, the materials in that object take up the energy as kinetic energy and move faster. If the average kinetic energy of the molecules in a substance increases, then the higher the temperature, showing that it is kinetic energy that determines temperature. In solids, kinetic energy is taken up in the form of vibrations and speed, so the molecules are seen to begin vibrating faster and more frequently, expanding the solid, which is seen when the temperature of a solid increases. On the other hand, in gases, the molecules just tend to whiz around at a greater speed, increasing the kinetic energy, which is seen through the increase of temperature. Okay, so how does temperature increase in a substance? And this can be explained by the idea of heat transfer. As the molecules move, they collide with one another, exchanging energy. The best way to explain this is through the idea of an iron rod with a flame on one end of the rod, and this shows the heat transfer through one end of the rod to the other. So the hotter parts of the metal are moving more quickly with more frequent collisions, while the cooler parts are moving more slowly. When a molecule with more energy collides with one less, they share energy more evenly. Faster molecules slow down and the slower ones speed up, distributing and transferring heat energy from one end to the other. However, heat is seen to be transferred differently depending on the substance being heated. Transferring the same amount of heat energy to two different objects will not necessarily cause the same rise in temperature in both. The effect that transferred heat energy has on the temperature of an object depends on three things: the amount of heat energy transferred, the mass of the object, and the specific heat capacity of the material from which the object is made. What is specific heat capacity? Specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of substance by 1 Kelvin. Different materials have different specific heat capacities because their molecular structure is different, and so their molecules will be affected to different degrees by additional heat energy, which explains why transferring the same amount of heat energy to two different materials might result in different temperatures being risen. To find how much heat energy is needed to raise the temperature of a material by a certain amount of degrees, we can use the equation E equals mc delta theta, where E is the amount of energy needed, m is the mass of the substance, C is the specific heat capacity of the substance, and delta theta is the change in temperature wanted or needed, so the rise in temperature which would be necessary for the amount of energy. You get it, right? And the units for the specific heat capacity is joules per kilogram minus 1, Kelvin minus 1, which you can get when you rearrange the equation to make C the subject. When heat is transferred to a substance, its internal energy also rises. But what is internal energy? Well as kinetic energy, each molecule has potential energy, which is its energy in relation to the other molecules in the substance, and it's the sum of the kinetic energy and the potential energies of all the molecules which gives the internal energy of the substance. The molecules do not all have the same amount of kinetic and potential energy, as the internal energy is randomly distributed across all the molecules, and this is shown in the Maxwell-Boltzmann distribution graph, which shows the number of molecules against the kinetic energy of the molecules in a substance. And this shows that the velocities of the molecules in the substance range from a few moving very slowly to a few moving very fast. So here it shows a few moving very slowly because they have a slow energy, while a few move very fast, which have a high energy. And it also shows that the majority are moving to a close of an average speed, which is around here. So most of the molecules are moving at an average kinetic energy. And we know that this is speed because since all the molecules have the same mass, their energies are directly dependent on their speeds. This graph is also for a specific temperature, so as the temperature changes, the graph changes, and the peak of the graph moves more towards higher energies, because the average speed would increase as the heat increases. So it's shown through this line. The Maxwell-Boltzmann distribution also shows that no molecules have zero energy, only a few molecules have high energy, and a few have slow energy as well, and no maximum value for the energy of a molecule can have. Oh, I can't read. No maximum value for the energy a molecule can have. So the energy can keep on increasing as long as the temperature is increasing. So they can keep on going this way forever. Okay. Yeah. Also, from the Maxwell-Boltzmann graph, we can figure out the molecular kinetic energy of a molecule, which is basically the average kinetic energy of any molecule in a gas state is proportional to the absolute temperature of the gas. And you can figure this out through this equation, which states that half m, which is the mass of the molecule, or the mass of the substance, times c squared, so specific heat capacity squared, is 3/2 kT, where k is Boltzmann's constant, which is 1.38 times 10 to the minus 23. And this isn't exactly very clear too, but that's a 2 and that's a 3. Yeah. Over the last 400 years, scientists investigating the physics of gases have determined a number of laws governing their behavior. The first of these was discovered by Robert Boyle, who was an Irish physicist, and this was known as Boyle's law, which states that for a constant mass of gas at a constant temperature, the pressure exerted by the gas is inversely proportional to the volume it occupies. So pressure is inversely proportional to the volume, and if this was put into a graph, it would look like this. So the higher the pressure, the smaller the volume. So if you keep on squeezing a basketball, for example, that has a hole in it, it will decrease in volume. And I think that's a very bad example. Another law, which was discovered about 140 years after Boyle published his law, was Charles's law. And this stated that for a constant mass of gas at a constant pressure, the volume is proportional to its absolute temperature. So volume is proportional to temperature, and this can be put in a graph which shows that volume is proportional to temperature. So the higher the volume, the higher the temperature. So, and as I had explained earlier when I was talking about temperature, the higher the temperature, the more a solid expands, which means the larger the volume. Another law, which is also known as the Gay-Lussac law, but is referred to more simply as the pressure law, states that for a constant mass of gas at a constant volume, pressure is proportional to its absolute temperature. So pressure is proportional to temperature. So the higher the pressure, the higher the temperature. And this can be put in a graph as shown here. The three gas laws are idealized and would work perfectly if we could find a gas which did not suffer from the real-world difficulties that real gases have. And there's a few laws which an ideal gas would have, and it shows the properties of an ideal gas. So the ideal gas laws is that the ideal gas would have molecules that have zero size, and that all molecules in the ideal gas are identical. No loss of energy in collisions, and collisions take 0 time to take place in an ideal gas. Molecules do not exert forces on each other except during collisions, and there are enough molecules that we can apply statistics. And assuming an ideal gas, we can combine the three laws to produce a single equation relating the pressure, volume, and temperature and amount of gas. It's not 4. Well, yeah. And this is shown, since I ran out of space, through the equation of states, which is PV equals N, Boltzmann's constant, T. And Boltzmann's constant, which we have looked at before, is 1.38 times 10 to the minus 23. And N is the number of molecules in a gas. And T must be the absolute temperature in Kelvin. Also, to make this equation more useful in practice, where we are dealing with very large numbers of molecules, we replace the Boltzmann's constant and the number n to obtain this equation, where n now is a small n, and it is the number of moles of the gas. And instead of Boltzmann's constant, we have R, which is another constant, which is universal gas constant, which is equal to 8.3 jkg minus 1 mole minus 1. And these can be used if we have an ideal gas. So with that is nearly the entire, I've covered the entire thermal energy unit, or at least I'm hoping I did. And this is a summary of everything, and it's so colorful. My hard work is so pretty.